You know, from a massive robot arm on an assembly line all the way down to the simple volume knob on your stereo, tons of machines need to feel their own movement with absolute precision. So today, we're going to dig into the simple but pretty brilliant device that makes it all possible, the incremental encoder. Let's get into how this thing actually works.
I mean, it kind of seems like magic, right? But the secret isn't some crazy complex software. A lot of the time, it's just a tiny sensor that's constantly, counting. The answer is this unsung hero of digital mechanics, the encoder. It's basically a device that translates physical motion into a language a computer can finally understand.
Okay, so let's start with the absolute basics. What exactly is an incremental encoder, and what's its main job?
At its heart, you can think of an incremental encoder as a translator. Its one and only job is to watch something spin, like a motor shaft or a wheel, and turn that rotation into a series of electrical pulses. But the key word here, and this is really important, is relative. It doesn't actually know its absolute position, just how much it has moved from wherever it started.
Now for the really cool part, how does it actually do that? How does it take simple physical rotation and turn it into a useful digital signal? Let's break down the mechanics.
Well, the design is just elegantly simple, and it's built around three core components. First up, you've got a light source, usually just an LED. Then there's a rotating disc with these evenly spaced slots cut into it. We call that a code wheel. And finally, you have a photosensor sitting on the other side just waiting to catch that light. And here's how it all comes together. That code wheel is attached to whatever's spinning. As it rotates, its slots either block the light from the LED or they let it pass right through to the sensor. And every single time the photosensor sees that little flash of light, boom, it generates an electrical pulse. So if you spin the wheel, you get this steady stream of pulses, like a digital heartbeat that perfectly matches the rotation.
So how do we get more precise measurements? Well, it's all about resolution. Take a look here. On the left, you've got a wheel with just 4 slots. That gives us 4 pulses for every single full rotation. But look over on the right, if we double the slots to 8, we get 8 pulses in that exact same rotation. Just like that, we've doubled our measurement precision.
And that's really the key. The more slots you can pack onto that code wheel, the more pulses per revolution, or PPR, you get. This lets the encoder detect smaller and smaller amounts of movement, which is what gives a robot arm or some industrial machine that incredible accuracy.
Okay, so we've got a great system for measuring how much something is turned, and even how fast it's turning, just by counting the pulses and how quickly they come in. But there's a huge problem, isn't there? With just one stream of pulses, how on earth can we tell if the wheel is spinning clockwise or counterclockwise? The solution to this puzzle is so clever, and it's what makes these encoders so incredibly useful. It involves using not one, but 2 pulse signals to build a much more complete picture of what's going on.
So here's the trick. Instead of one sensor, we use 2, and they're just slightly offset from each other. This creates 2 separate pulse signals, which we call phase A and phase B. Now, because of that offset, the signals are out of sync. When the wheel spins clockwise, you'll notice the phase A pulse rises just a little bit before phase B. But if it spins counterclockwise, the order flips.
The logic is just beautifully simple. As the source material puts it, the direction is determined simply by which pulse, A or B, rises first. That is the entire key right there. So, to put it super simply, the system just has to look at the sequence. If it sees A, then B, it knows it's turning, say, clockwise. If it sees B, then A, it knows it's going counterclockwise. That's it. Problem solved. So clever. Okay, so let's pull all of this together. We've got these 2 streams of pulses, A and B. What exactly can we learn from them?
From just these 2 simple signals, we get a huge amount of information. The total count of the pulses tells us the relative position, or how far it's moved. The frequency of those pulses, how fast they're showing up, that tells us the rotational speed. The order of the phases, whether it's A before B or B before A, gives us the direction. And of course, the number of slots, the PPR, that determines our overall precision and accuracy.
But, for all of its cleverness, the incremental encoder has one major blind spot. When you first turn it on, it has absolutely no idea where it is. It only knows movement from that starting point. And that's why a lot of machines have to do that little homing sequence when they power up. They have to move to a known physical switch just to set their 0 point. And that brings us to our final and really big question. This whole limitation is a pretty big deal in a lot of applications. So what if a machine absolutely needs to know its precise, exact position the instant it powers on, without any homing at all? How is that achieved? Well, that's a story for another explainer.